Hello again. Today we're going to be talking about the binding energy. You see everything, all the elements in the periodic table, they have different number of electrons in different positions and different energy levels, different sublevels, different orbitals. But there's something called binding energy which is often used to describe, to better explain what's happening inside atoms. So take a look at this. This is the atom of lithium. So it's got 7 nucleons, which means 4 neutrons and 3 protons. So see, the protons are red. Remember, each proton is positive and the electrons are blue and they're negative. And remember, the electronic configuration of lithium is 1s2. So in the first energy level, it's got only these 2 electrons. Please remember, they do not move in a circle. We often put them in a circle to show that they're closer to the nucleus than the second energy level. So this is 2s1 orbital of lithium. So they has 2 electrons in energy level 1 and 1 electron in energy level 2. What's the difference between them though? See, one of the reasons why the electrons move around the nucleus is because of the Coulomb force. Coulomb force just means simple attraction between a plus and a minus. These 2 electrons are unable to escape the pull of the nucleus because they are negative and the protons inside are positive. And we talked about this already when we talked about atomic radii. So if there are more protons here, these will actually get closer, right? But that's not the point here. The point here is this. When you compare these 2 with this one, which one is more bound to the nucleus? Of course, these 2 are closer to the nucleus, so the minuses are closer to the plus. So they're more bound to the nucleus, while this one is more free. It's less bound to the nucleus. This binding, this how much something is bound to the nucleus is described by binding energy. So we say that these 2 electrons closest to the nucleus have higher binding energy, which just means they're more connected, more bound to the nucleus. And this one has smaller binding energy just because it's more far away. So it has more kinetic energy, but less binding energy. So if you add a little more energy, it will achieve enough energy to escape, right? So again, bigger binding energy, these 2, this smaller. Now, knowing that, check these out. These are the questions that they often give in AP. There are only a few examples on these websites. I just use them to just describe the situation for you. I will give you an actual AP question test from this very soon. So this is something called a photoelectron spectrum. Again, it's a machine where you put a sample, an element, and it spits this out. So see here on the x-axis, you have binding energy. That means that this represents something which has a higher binding energy, it's closer to the nucleus, and this has a lower binding energy, and this has even lower binding energy. And here you see it says relative number of electrons. So just by using logic, if these are the electrons, if these peaks represent the electrons, the position of the peak here on the x-axis means that if something has a higher binding energy, it must be closest to the nucleus. So this is the closest to the nucleus. So this is simply 1s orbital, right? This is the first energy level. And it's got 2 electrons, which means that since this is relative number of electrons, this is 1 electron, there's 2 of these lines, and then 2 electrons. So this is just 1s2. So what is this then? The next closest, it's 2s2, right? And this should be 2p, but it doesn't have 6 electrons. Why? Again, simple. The size of this peak means that these are 2 electrons. So if this were to be 6, it will have to be 3 times higher than this. But it's not. It's only about 50%. So that means there are only 3 electrons in the p orbital. So we can easily determine, see, the question is what element is illustrated. So we already determined here we got 1s2 orbital, and then 2s2, and then 2p3. 3 orbital. And again, this corresponds to this, so this is 1s2, 2s2, 2p3. Simple. And then we just need to find this on the periodic table. How we can do that in many ways. First of all, the last energy level is 2, so it's in the second period. It has 5 electrons, the last energy level, so it's in group 5. If we look at that second period, group 5, this is nitrogen. We can even have a check because the total number of electrons here is 7, which means the total number of protons is also 7, which means that the atomic number is 7, and that's nitrogen. So let's see. I hate that the answers are open. Wait. Take a look at this. First, let's forget what's the question and just analyze this. See, there are 2 elements on this spectrum. Sodium, magnesium. So see, sodium is blue, magnesium is purple. And then you can see that this, because this has the highest binding energy, it's obviously an s orbital, and it's full for both magnesium and sodium. So this is 1s2 for magnesium, this is 1s2 for sodium. Well, why is there a difference? Well, again, the same explanation as that we use for atomic radius. So magnesium, the difference between sodium and magnesium is just magnesium has 1 more proton, 1 more electron. Here the protons are the key. So the reason why this one has a higher binding energy is because magnesium has 2s orbital, 2s electrons, which are closer to the nucleus. Why they're closer to the nucleus? Because magnesium has 1 more proton compared to sodium. So that's why there is a difference here. However, look at this difference. This is obviously, these two are obviously 2s sublevels of sodium and magnesium. But now the difference is not this big. Now the difference between them is smaller. Why is it smaller? Well, again, a simple explanation if you imagine this. So the second energy level is above the first energy level. So in the first energy level we have 2 electrons which shield the upper electrons a little bit from the influence, from the positive influence of the nucleus. So the more far away that you go, the closer the 2 elements will get. Why? Because the first energy level electrons shield the upper electrons from the influence of the nucleus. And then if there are 2 energy levels, then the third energy level is even more shielded. So as you go higher, this difference in peaks for different elements will be smaller. But let's see what the question is asking. Using the PES spectra, this is just photoelectron spectrum, what answer explains the differences in the position and intensity of the 3s peaks between Na and Mg? So here they're only asking the difference, about the difference in the position for just this peak. We just observed 3s. 3s is here, and you can see they're very similar, but they're not the same. You can see sodium has 1 electron, that's why the peak is smaller. And magnesium has a little bit bigger binding energy. Why has bigger binding energy? Because it has more protons. So we need to find an answer that explains that. Greater shielding effect. So there is a shielding effect, but that doesn't explain anything here. They're asking why they are different. That's not, this is the answer to why the difference is smaller, but they're just asking us about 3s. None of the above. The Mg is larger in size, making the electrons, and doesn't have anything to do with size. Na experiences a larger effective nuclear charge. No. So Na has 1 less proton, so smaller charge. And let's see, Mg experiences a larger effective nuclear charge. Yeah, I mean, I'm not even looking. So yeah, Mg has a larger effective nuclear charge. That just means more protons. So we're correct here. Now, let me show you another interesting one. And again, you'll have questions about this. Look at this one. Here we have which of the following best explains the difference in signal intensity for the 2 peaks. The photoelectron spectra of 2p electrons of oxygen and chlorine. So see, here they give us just 2p. This is just 2p. And let's check out chlorine and oxygen. So oxygen has 2p and chlorine has 2p, and above it even has 3p. But it says here, look at this, this is a cheeky question. the difference in signal intensity. Signal intensity means the size of the signal. This, how big this is. That's very easy to explain because chlorine has more electrons. That's it. So oxygen has how many 2p electrons? Let us see. So oxygen has 8 electrons. So that means 1s2, 2s2, and 2p4. So oxygen has 4 electrons. So these are 4 electrons. And chlorine has how many? 1 more. So basically, we don't even, actually, it's not 1 more. Let me write it down nicely so we can, I'm trying to make this fast, but apparently it doesn't work. So let's see. Oxygen, 8 electrons. 1s2, let's say oxygen, 8. 2s2, 2p4, yes. And then you got chlorine, which is 17 electrons. That's going to be a long one, and my cat is, hey, get away. 1s2, 2s2, 2p6, that's 10. 3s2, 3p5, that's 17. So they're asking us to compare this and this. Remember, this is just 2p orbitals. So 2p orbital of oxygen has 4 electrons, and 2p orbital of chlorine has 6 electrons. So it's pretty clear that this one should be, what, 50% higher, because this is 1, 2, 3, 4 electrons, right? In 2p, see? And this is 1, 2, 3, 4, 5, 6 electrons. Not possible. Oh yeah, yes, of course, 6 electrons, because we're not looking at 3p, we're looking at 2p. So 2p has 6 electrons. So 1, 2, 3, 4, that'll be this. 1, 2, 3, 4, 5, 6, that'll be this. So the answer here is, what explains the different signal intensity is just that chlorine has more electrons in the 2p orbital. Let's see. Oh, incorrect. Okay, here it's already explained. Chlorine has more electrons in 2p orbitals. I like to say orbitals, but p again is technically a sublevel or subshell, so that's a better way to say it, definitely. Okay, practice these, I'll give you more.